Good afternoon, children. We are back in our chemistry online class. In yesterday's class, we had started discussing about standard hydrogen electrode. We had not yet completed the discussion of the standard hydrogen electrode, which is shortened as SHE. See, a standard hydrogen electrode is shortened as SHE. Okay, S for standard, H for hydrogen, E for electrode. Now, it is actually a type of reference electrode. It is a type of reference electrode, and its reduction potential is arbitrarily assigned as 0 volt at all temperature. What is the meaning of arbitrarily? That means it is been given a potential of 0, because we have to calculate the potential of other electrodes in reference to She. We have to calculate the potential of other electrodes in reference to She. So its reduction potential is arbitrarily given as 0. Okay, now the next thing is that the standard hydrogen electrode consists of a platinum electrode coated with a platinum black. We have a platinum electrode that is coated with platinum black. The electrode is dipped in an acidic solution having 1 molar concentration of hydrogen ion. So what is happening? The electrode is dipped in an acidic solution having 1 molar concentration of hydrogen ion. Having 1 molar concentration of hydrogen ion. Okay, pure hydrogen gas at 1 bar pressure. Pure hydrogen gas at 1 bar pressure is continuously bubbled through the solution. Okay, pure hydrogen gas at a pressure of 1 bar pressure is continuously bubbled through the solution at a temperature of 298 Kelvin. At a temperature of 298 Kelvin. Okay, the temperature selected is 298 Kelvin. Can you see the adjoining diagram? In the adjoining diagram, what we could see that we have a trough-like structure. In this trough-like structure, we have taken HCl, whose strength is 1 molar. Okay, and we have a platinum foil, right? This platinum foil is coated with platinum black. It is covered by a tube. At the beginning of the tube, we have an entry point where hydrogen gas is been allowed to pass at a temperature of 298 Kelvin and a pressure of 1 bar, atmospheric pressure. Okay, this is the total setup of this. This is the total setup of the standard hydrogen electrode, or which is called She. Okay, now see, the hydrogen electrode can act both as a anode or as a cathode depending on the nature of the nature of the electrode in which it has to be attached. So just remember. So have you understood now? So what is actually happening here? We have a anode that is being connected with that. See how it is acting as an anode and how it is acting as a cathode. If it is acting as an anode, that means it is releasing the electrodes. It is releasing the electrons and forming twice H plus ion. Okay, and acting as a cathode, it is accepting to electrons and forming hydrogen gas. So this is the basic difference when it's acting as a anode as well as acting as a cathode. Okay, now when we represent it in this way. We have platinum. Okay, as it is the platinum electrode separated by hydrogen, then this one hydrogen ion and molar concentration we mentioned over here equal to 1 m. If you want to copy it down, please copy it. Then I would move to the next topic of today. If you want to copy it, please copy it, children. I hope you are copying it, children. After that, we have the next part of the chapter, that is standard electrode potential. What is the meaning of standard electrode potential? See, standard electrode potential may be defined as the electrode potential of an electrode determined relative to the standard hydrogen electrode. Okay, that is in reference to the She, that is standard hydrogen electrode. What we measure as the potential of the electrode is called the standard electrode potential. Okay, under a standard condition, and the standard conditions are taken as follows. What are the standard conditions? See here, the concentration should be 1 molar. That is, we have mentioned that the concentration should be 1 molar in each ion in the solution. That is, whether we are taking the She or the electrode whose potential we have to calculate, it should have a concentration of 1 molar. That is the first point. Second, temperature is restricted to 298 Kelvin. Temperature is restricted to 298 Kelvin. And third is the pressure for each of the gas is 1 bar atmospheric pressure. So what I'm mentioning over here, that is the standard condition where we calculate the standard electrode potential. We actually have to see that the concentration should be 1 molar, the temperature should be 298 Kelvin, and the pressure in which the gases has to be kept there is actually 1 bar atmospheric pressure. In that 1 bar atmospheric pressure, we can only calculate the standard electrode potential. So have you understood now? I'm repeating it once again. When we have to calculate the standard electrode potential, it is defined as the electrode potential of an electrode determined relative to the standard hydrogen electrode. In reference to the standard hydrogen electrode, what the potential we measure becomes the standard electrode potential. Okay, and the standard conditions taken are, we should take the electrode in which the concentration of the ion should be 1 molar, temperature should be 298 Kelvin, that is 25 degrees Celsius, and the pressure should be 1 bar or 760 mm of Hg. Okay, this is the pressure that should be applied. So I'm giving you 2 minutes time. Please copy it down. Then I would move to the next part of the chapter. I hope children you are copying it. Okay. After that, we are discussing the next part, that is cell potential or EMF of a cell. We are discussing the next part, that is the cell potential or EMF of a cell. EMF you write electromotive force. EMF you write is the electromotive force. Now what is that EMF of a cell? The EMF of cell actually tells you, the EMF of cell actually tells you that it is the difference between the electrode potential of the two half cells. It is the difference between the electrode potential of the two half cells is called cell potential. It is known as electromotive force of the cell if no current is drawn from the cell. It is known as the electromotive force of the cell if no current is drawn from the cell. Now we have cell potential or EMF. So cell potential or EMF of a cell, that is, it is the difference between the electrode potential of the two half cells, is called the cell potential. It is known as electromotive force or EMF of the cell if no current is drawn from the cell. If no current is drawn from the cell. So here you write down that cell potential or EMF of a cell is the difference between the electrode potential of the two half cells, is called cell potential. It is known as electromotive force of the cell if no current is drawn from the cell. If the condition is such that no current is being drawn from the cell, in that case what we do, we actually find out the difference between the electrode potential of the two half cell. Okay, we calculate the electrode potential of the two half cell, which is actually called the cell potential or EMF of the cell. It is known as electromotive force of the cell if no current is drawn from the cell, and it is given by this equation. Well, I think you can see this equation. E cell, that is the electrode potential of the that is the EMF of the cell, equals to E reduction, that is cathodic, minus E or reduction anodic, or equal to E cathode minus E anode. Okay, that is, it is the difference between the electrode potential of the two half cell. One is the cathodic half cell and the other is the anodic half cell. We know that two half cells, one part there is cathode and the other part there is anode. So one is the cathodic half cell, other is the anodic half cell. So the basic difference between these two is called the cell potential, or the EMF of the cell is called the cell potential or EMF of the cell. I'm giving you 2 minutes time. Please copy it, children. I hope you have copied it, children. Okay. Now we are moving to the next part of the chapter. Now we are moving to the next part of the chapter. But before we move, I want to revise what we had discussed till now. We have discussed till now standard hydrogen electrode. Then we have discussed about standard electrode potential. Then we have discussed about EMF or the cell potential. Okay. Now in the next part of the chapter, how we represent it? We represent it this way. Since, see here, since anode is put on the left and cathode is in the right, it is represented by this way. E cell equal to ER minus EL. Okay, ER minus EL. Can you say it? ER minus EL. Or we can just write for a Daniell cell, E cell 0 equal to E0 copper plus 2 by copper into E cell zinc plus 2 by zinc, whose value comes to 0.35 0.34 volt. Okay, minus that comes to 1.10 volt. Now we have the next part, the most important part, that is called the Nernst equation. The next part of the chapter we have the Nernst equation. Okay, next part of the chapter we have the Nernst equation. Now what is this Nernst equation? See here, according to the Nernst equation, it relates the electrode potential with the concentration of the ions. It relates the electrode potential with that of the concentration of the ions for an electrode reaction. Can you just see the electrode reaction is just like this. Mn, accepting n number of electrons, that gives the metal M, right? Now Nernst equation can be written as em plus n by n equal to E0 m plus n by m. Ultimately, this is the equation we are getting when you substitute the value of log. It comes to like this. Okay. Then the electrode potential we have, and correspondingly substituting the values we get these values. Okay, so ultimately we substitute the values of R and F and we get this as the value. E cell equal to E 0 cell 2.303 by NF RT log concentration of the product by the concentration of the reactants. Okay, this is how we get the Nast equation. This is, children, how we get the Nast equation. Okay, I hope you need to copy it down. I'm uploading a part of the book which you can copy if you don't have the notes with you. Okay, see here. We have the calculation of the cell potential using the Nast equation. Okay, see, let us apply this equation. Okay, we have the zinc and zinc plus 2 and the copper plus 2 and copper half cells. Okay, now the cell potential is E cathode minus the E anode, right? Now when we have the E cathode minus the E anode, we substitute the values. So Nast equation for the copper electrode is given by this one. Okay, next we have for the zinc electrode we have this one. Okay, now substituting these values we get the values as like this: 0.059 by 2 into log copper plus 2. So if you want to copy, children, plus just copy it down. I hope, children, you are copying it. After that, we'll move to the next topic, that is EMF and Gibbs free energy. How we can calculate the EMF and the Gibbs free energy. I hope, children, you have copied it. Okay. After that, we are discussing the next topic, that is EMF and the Gibbs free energy. We are discussing the next topic, that is EMF and the Gibbs free energy. So the next topic we are discussing is EMF and the Gibbs free energy. See here, the work done by a reversible galvanic cell is equal to the decrease in its free energy. So I can say that the work done by a reversible galvanic cell is equal to the decrease in its free energy. Okay, that is the work done. That is the work done by a that is the work done by a reversible galvanic cell is equal to the decrease in its free energy. Mathematically, it is represented as del Rg equals to negative NFE cell. NFE cell, okay, where each of these letters have their own values, okay. Each of these letters, they have their respective, each of these letters have their own respective values. Right, children, have you understood it? Each of them has their own respective values, right? Now, when in the same equation we write if the concentration of all the cell reacting species is unity, that is, if the concentration becomes 1, then the same equation turns E cell equal to E0 cell, and we get del RGC in the same equation we are substituting equal to minus NFE0 cell. Just compare this to equation. I'm repeating it once again, that when we have to calculate the EMF and the Gibbs free energy, what we do, the work done by a reversible galvanic cell is equal to the decrease in its free energy, okay, is equal to the decrease in its free energy. So have you understood this part? After that, you see mathematically it is represented by this equation del Rg equals to negative NFE cell. Okay, if concentration of all the reacting species is unity, then in that case E cell equal to E0 cell, or we can just write del Rg 0 equal to minus NFE 0 cell, where del Rg0 we can calculate the equilibrium constant of a reaction, or we can just write del Rg equals to minus RT ln Kc. Kc, you know, molar constant at the concentration, okay. Now when you substitute the value del Rg0 equals to negative 2. See, make one correction, it is 2.3. Make this correction, 2.303 RT log Kc. Okay, so log Kc and Kr, Kp, you know these things. You have already been taught this in class 11. Okay, Kp, Kc you have discussed. You know these things. Molar concentration at, that is at constant pressure and at constant volume. Okay, so that is about the EMF and the Gibbs free energy. I hope you are copying it. Giving you 1 minute time, please copy it down. I'm telling you, students, these are very, very important for exam point of view. These mathematical derivations are important because based on these equations, problems would be asked. Okay, based on this type equation, problems would always be asked. So make sure you understand this calculation and these derivations. Okay, after that we have the next part of the chapter. The next part of the chapter is concentration cells. What are concentration cells? If two electrodes of the same metal are dipped separately in two solutions, okay, of the same electrolyte having different concentration, and the solutions are connected through a salt bridge. Such cells are known as concentration cells. I'm repeating it once again. If two electrodes of the same metal are dipped separately in two solutions of the same electrolyte having different concentration, okay, and the solutions are connected through a salt bridge. We know that in a cell, galvanic cell, we have the oxidation half cell, we have reduction half cell. Each of them is connected by a salt bridge, okay. But suppose, remember that we have two separate electrodes, but the electrodes are made up of the same metal. Suppose I have both the electrodes made up of copper, or I have both the electrodes made up of zinc, okay, and they are connected with each other, but to two separate salt solution. Two separate salt solutions means same salt, but the concentration is different. Mind it, I'm repeating it once again. We have two electrodes which are made up of the same material, right? Although they are made up of the same material, but they are dipped in an electrolyte that is made up chemically of the same compound. That is, suppose I have dipped copper in a copper sulfate solution, but the copper sulfate solution for both the electrodes are not the same. One is having a higher concentration, one is having a lower concentration. Or I can say in other words, they should not have the same concentration. If they have the same concentration, then we cannot calculate this type of concentration cells. Okay. See the example over here. We have hydrogen in H plus ion with C1 concentration, we hydrogen H plus again in H2. Okay, these are the way we are connecting. We have the same hydrogen gas that both of them are inserted in a solution of an acid having the same hydrogen ion, but the concentration is not same. One is having a higher concentration, obviously other is having a lower concentration. Okay. Now suppose another example, they have given you copper and copper plus 2 C1 concentration. The next one is copper plus 2 in copper with C2 concentration. So what is happening? Both the electrodes are of same material. They are dipped in the same salt solution, but where lies the difference? The difference is their concentration is not same. I'm repeating it once again, children. Try to understand. In a concentration cells, what we do, we take two separate electrodes, okay, but mind it, the separate electrodes are made up of the same metal. See, they are made up of the same metal, right? And these electrodes are dipped in two separate solutions, but the solutions are chemically identical, but their concentration is different. Suppose example, I can tell you that we have taken two copper rods, right? One for the oxidation cell, other for reduction cell. Both the cases we have the same type of copper rods, both are identical in all aspects. Both these copper rods are dipped in copper sulfate solution. I'm repeating once again. Both of them are dipped in copper sulfate solution, but the concentration of the solution is different. Concentration is not of the same type. So what have I taken? I have taken two identical copper rods, right? They are having the same weight, same mass, everything. Both of them are identical to each other. They are both being inserted in two separate chambers of copper sulfate. So copper rod is dipped in copper sulfate solution. Although up till this much it looks they're identical, they are actually not identical. What is happening? We are having these two separate ones. As we are having these two separate ions, but mind it, the concentration of the solution is not same. Concentration here is different. As the concentration is different, so what will happen? They are connected by a salt bridge in order to connect both the half cells. Such type of cells are called as concentration cells. So here you can see that the EMA for concentration cell at 298 Kelvin is given by this equation. Zinc plus 2 equilibrium with zinc plus 2 zinc. So E cell equal to 0.0591 by n into log C2 by C1, where I can tell that C2 is greater than C1. I've told in the beginning that when we are taking this type of salt solution, both of them should not have the same concentration. Their concentration varies from one to that of the other, right? Please copy it down. Then we would see now how it is been represented. E cell equal to 0.591 by n into log C2 by log C1. Okay, E cell equal to 0.0591 by n log C2 by C1, where I can say that C2 is greater than C1. C2 is greater than C1. So this is how the constant condition of a concentration cell looks. I'm giving you 2 minutes time. Please copy it. I hope you are copying it. After that, children, we are going to discuss about electrolysis, commercial cells, and the process of corrosion. What is electrolysis? Electrolysis is actually the process of decomposing of an electrolyte when electric current is passed through its aqueous solution or fused state. Suppose I'm telling you one example. We have sodium chloride. You have seen sodium chloride at your home, that is a solid crystalline powder. If you want to pass electricity through it, you will see electric current will not pass. But if you take the same sodium chloride, you melt it, right? It becomes actually fused sodium chloride. Now with this fused sodium chloride, if you connect it to a circuit, what will happen? Electric current will pass through it because it allows the passage of electric current. Through it. Okay. Have you understood, children? Now see, the next part we are having is suppose I make an aqueous solution of sodium chloride. Through this aqueous solution also, what I know, that electric current will pass. Why electric current will pass? Because aqueous solution is a excellent conductor of electricity. Aqueous solution is excellent conductor because in the aqueous solution ion formation takes place, and that's why, see what definition they have given you: the process of decomposition of an electrolyte when electric current is passed through its aqueous solution or fused state. Either in its aqueous solution or in its fused state, it is the process of decomposing of an electrolyte when electric current is passed through its aqueous solution or that of its fused state. Okay, this is called electrolysis. Now see the next part. The process of electrolysis of a substance is governed by Faraday's law of electricity. Now see this process of electrolysis. Here we have to follow certain rules. And what are those rules? These rules are called Faraday's first law and Faraday's second law. I'm repeating it once again. Electrolysis is a process in which a salt or that of a aqueous solution of a salt or the fused salt, when electric current is passed through it, it splits into its constituent ions. But the process of electrolysis is conducted by, when conducted, we have to follow certain rules, and these are the rules. This was given by Faraday, and hence it is called Faraday's law of electrolysis. Okay, and we also know that this law is that there are two laws: the first law and that of the second law. Now what is the first law? According to the first law, you see, amount of any substance deposited or liberated at the electrode is directly proportional to the quantity of electricity passed through it. See, whenever electric current is passed through an electrolyte, what happens? The electrolyte splits into its constituent ions, right? These constituent ions will migrate either to that of the cathode or to that of the anode. If it is a cation, that will migrate to the cathode. If that is anion, that will migrate to that of the anode. Okay. So according to Faraday's first law of electrolysis, it tells you that amount of any substance, that is how much amount of the substance would be deposited at the cathode and how much amount of the substance would be deposited at the anode, that is governed, that is directly proportional to the quantity of electricity passing through it. That is, larger amount of electric current you pass, larger would be the deposition. The lesser amount of electric current you pass, lesser is the deposition. I'm repeating it once again. Faraday's first law of electrolysis states that amount of any substance deposited or liberated at the electrode is directly proportional to the quantity of electricity passing through the electrolyte, directly proportional to the electricity directly passing through it. Okay, see the statement. So if I say, if I have W grams of a substance which is deposited on passing coulombs of electricity, then I can write W directly proportional to Q, or W equal, or I can write, if I substitute Q, because Q equals to I into T. So I can write W directly proportional to I and T. I can write W directly proportional to I and T. Or if I want to remove the proportionality sign, I put a constant Z. That Z is called as the constant of proportionality, and it is called electrochemical equivalent of the substance. It is called the electrochemical equivalent of the substance. Okay. It is called the electrochemical equivalent of the substance. Okay. And Z is a constant of proportionality and is known as electrochemical equivalent of that substance. So if you want to copy it down. Okay, children, I'm repeating the law once again. Faraday's first law of electrolysis tells you that amount of any substance deposited or liberated at the electrode is directly proportional to the quantity of electricity passing through the electrolyte. Okay, or if I say W grams of a substance is deposited on passing coulombs of electricity, then I can write W directly proportional to Q, or W directly proportional to I into T. Okay, where T is the time, I is the current. Okay, now we can write W equals to Z into I into T, where Z is the constant of proportionality and it is known as electrochemical equivalent of the substance deposited. Okay. Okay, children, that was all for the day. We will meet in the next week. Have a nice weekend ahead. Thank you.